Okay, lesson 5 on functions. This is the last lesson on functions. Okay, example 1. The Carter family are driving to the Yukon for a family vacation. The graph represents the amount of fuel in liters in the gas tank of their car on the first day of their journey. So it's divided, the graph is divided into 8 segments, and it says, explain what's happening between A and B. Well, what I see in A and B is that time is moving forward and the amount of gas is dropping steadily, so they are driving at a constant speed. And then from B to C, they're stopped for a break of some sort. And then between C and D, that the gas tank, the amount of fuel in the tank is going up very rapidly, so they're refilling the tank, refueling. Okay. What is the rate of fuel consumption in liters per hour between D and E? All right, so the time between D and E is, let's see, 12, 13, 14, 15, 16, 17. So each of these is 1 hour. So we have 1, 2, 3.5 hours. So the rate of consumption is liters per hour. So remember, if you were with me for all the ratio stuff last year, I nagged you and nagged you and nagged you about putting your units down or writing down what it is you're doing. Hopefully that stuck. So we've got our hours is on the bottom, so that's going to be 3.5 hours. And how many liters did we use in that time? Well, at B, we're at 60 liters, and at E, I'm going to call that 25 liters. So 60. Okay, apparently you can't scroll at the same time you're writing on it, or it does not work. Okay, 60 minus 60 minus 25 equals 35. So that's going to be 35 liters in 3.5 hours. And if I just do that division, 35 divided by 3.5, I get 10 liters per hour. Which segment represents the car being fueled for the second time? Well, that would be this other time when it goes up really quickly, so that's GH. And calculate the total time when the car was driven. Well, there's 2 ways. We could add up all the pieces, or we could do the total time minus the pieces where it wasn't being driven, which is what I would do. So this one is like, this is like a half hour, and this is a 1 hour. And they went from, let's go there, so from 7 to 17. So they drove 10 hours. So it would be 10 hours minus the breaks. And the breaks were 1/2 plus 1 is, we can go 1.5. So 10 minus 1.5, that equals 8.5 hours. And then the fuel costs 85 cents per liter. How much fuel did it cost? So how much did they use? Well, from A to B, they used fuel from A to B. Okay, I can't be looking at both things at the same time, so I'm looking at my paper. So you should be looking at your paper. So they used fuel from A to B, and then they used fuel from D to E, and they used fuel from F to G, and they used fuel from H to I. So we need to figure out how much fuel they used in that time frame. So from A to B, it starts at 50, and it goes down to 20. And then from D to E, at D, it's at 60, and it goes down to 25. And from F to G, for F it starts at 25, and it goes down to 15. Could have actually done those two as a a constant amount, but I didn't see that the first time. That's okay. And H goes from 60 down to 50. So we use 30 liters here and 35 and 10 and 10. And if I add that all up, I get 85 liters of gas was used. And then 85 liters times $8.85 per 1 liter. That equals $72.25. That's how much they spent on gas the first day. Okay. I don't know where you find gas for 85 cents a liter, but not this year. Okay, there you go. That's that first page. Okay, next page. Suggest a possible scenario for each of the following graphs. I'm going to do this one first, B, because there's actually not a lot of things that do that where the speed does that, because this is the speed. Like you look at this and you might think of a bouncing ball, but the bouncing ball is actually going to be the opposite way because it's, oh, maybe not. It could be, but it's upside down. Like this is when it bounces, it's going fastest when it bounces, and then it goes up. No, I don't think that's right. I think it slows down more gradually than that. I think a bouncing ball would be more like, okay, speed, time, speed. When I drop it, it starts at 0. No, when I drop it, it starts at 0. Never mind, never mind. Anyway, let's just call this a pendulum. Okay, a pendulum swinging back and forth. You know, it starts at the top. It's not moving at all. So I'm going to make my pen the pendulum. So it starts, it's not moving at all, and then it speeds up, and then it's going really fast, and then it slows down to nothing, and then it starts off at nothing, and it goes speeds up, and then it's going really fast, and then it's slowing down. So that's what the pendulum. That's that one. This one, there's all kinds of things that you could do. So it could be, so this is the speed and the time. So the speed is constant. So something's moving. So it's a car driving, okay? And then it's slowing down at a constant speed for, I don't know, construction or whatever, they're sightseeing. And now they're moving at a slower speed for a while, but a constant speed. And then they speed up a little bit, and then they're moving at a constant speed again, and then they slow down to a stop. So on the notes, you can see that I've written this part is a car traveling at a constant speed, slows down for a construction zone, steady speed through construction zone, speeds up after construction, steady speed but slower than before, and slows to a stop at lights. Okay? Just make up something that makes sense. Okay, there's thousands of things that would work for that. Just you are moving the entire time until you get to the end because you do have a speed that's non-zero. That's the tricky thing there. Okay, sketching a graph. I don't like these ones because these actually I think come out fairly similar. You turn the oven on. It takes some time to. Oops, it heats up. I assume it heats up at a fairly constant temperature, and then you're baking your pie, so it's going to just stay at the same temperature for. Oops, that was not very good lying for same temperature. So it stays at your constant temperature for a while. And then you turn the oven off and it takes a while to cool off. Oh, I know, wait a minute, this was wrong. That's what I remember this now. Okay, it actually starts at 20 degrees because your oven starts off at room temperature. It doesn't start at 0, right? My notes are wrong on this one. I have to fix that. So the oven heats up slowly, stays at a constant temperature, and then it takes longer to cool back down to room temperature than it took to get up to baking speed, and then it's going to stay at room temperature. Okay, there. Whereas somebody running a 100-meter sprint, well, if you're running, you're going to start from 0. You're going to start off really fast. You're accelerating really fast to get your maximum speed. Ideally, you are running flat out for the entire race, and then you slow down, not as fast as you started, but you don't just stop all of a sudden, right? Like you run those couple of steps where you're just going slam, 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 slam on the floor. Okay, that's it. That's the end of this lesson. Bye.